Okay, so welcome back to another video. So here today we have a special alternating infinite sum, and that is we have that, the sum is -1 to the power 1 plus 2 plus all the way up to plus n, and then divided by 2n plus 1 quantity square. So I think if you notice that the exponent specifically, this is written as the sum of the n natural numbers, and it has that nice close formula of n times n plus 1 divided by 2. So that's actually a first, giveaway on where to start, rewrite that sum into using that substitution. And then as we proceed forward from here, there's actually going to be a lot of rearranging, specifically when it comes to reindexing these sums. This is actually going to take a little bit of a neat creative approach on how to evaluate the sum. But with that in mind, there's also going to be a couple of special formulas / functions that will help utilize, evaluating the sum as well. So there's not much to it. The best, obviously, I think the best way to start is by noticing that, as mentioned, the exponent can be substituted for the sum of n natural numbers, and then we can actually work the way from there slowly, one at a time. So with that, let's actually just jump right in. So as notice, I'll first write that 1 plus 2, our exponent specifically, all the way up to plus n, is our special formula for the sum of the n natural numbers, so that's divided by 2. So I'm going to write s as our given sum, and I'll put in that new substitution. And so we're going to have that so far. This is the infinite sum of -1 to the power n times n plus 1 divided by 2. All this being divided by 2n plus 1 quantity square. You notice I wrote that equals next because what I'm going to do now, we're going to actually do a little bit of a creative approach. And what I'll do is I'll separate our indices in terms of separating from one that's grouping with the odd terms and then another one with the even terms. So that means we have a sum of two sums. So first, our indices dealing with odd of the same series we're dealing with. And then another one we're dealing with is the sum of the even terms of the same series as well. And so from here, there's actually going to be some substitutions that we're going to be doing over here. So let's actually do that. So I'll put this on the top over here just to utilize the room, and then we can continue forward from down here. So what I'll notice is that, of course, if we have that we're dealing with odd integers or odd terms and even terms. So for the first part, I'll let specifically for n is an odd number. Let's suppose that we'll let n equals 2k plus 1. And so from there, what I'll do is now just starting with our, of course, this is going to be our odd. So our odd terms of the infinite sum of the alternating series, that substitution that we just, separated out by, and then 2n plus 1 square. What we'll see is that now everything for the odd terms that we put in, we're going to put this for the new terms for k. And it's actually going to start from 0, and then it actually goes to infinity for all of the odd terms we're taking into account with. So this means that we're going to have -1 to the power k plus 1, and then all this divided by, so this will be 4k, and then add this with plus 3 quantity square. And I know what you might be thinking. You can see that if I just put n for 2k plus 1 back into here, and so we get the denominator. But how does that make sense with the alternating sum of the numerator? Because it doesn't match up if you were to do that substitution. Well, this actually has to apply more of, you're going to have to play around with some numbers. Well, as we see that if I let n equals 1, for example, so if I just plug this back in, so 1, and then, so that's 1 times 2 divided by 2, so it's going to be a 1. So that's actually going to be an odd degree over here. And then what you'll notice is that if we set that n is equal to 1, so k would be 0 starting with this new index, and we just plug this back in, we get that that's an odd degree. Try another number. Let's say 3, for example. So 3 times 4, 12 divided by 2, 6. So we have an even degree, okay? So, and now if I say that for 3, then that means we have to put in k is equal to 1, so k is equal 1. So k plus 1 is 2. That implies that that's going to be even degree on the, for the numerator. You just have to keep playing with these numbers and then notice a pattern over there. So it actually does match. Similarly, if you do the same thing for the even numbers, so let's see, if I say for n is even, then we let n equals 2k, all right? So now everything here would be written as follows. So we have our the infinite sum, or rather for n is an even term of our same, the series from just like we separated out, n plus 1, then divided by 2. All this being divided by 2n plus 1 quantity square. So we see that all the indices now will actually can start from k is equal to 0 and then go all the way up to infinity. And so with this new term, so we have this is -1 to the power k and then divided by. So applying that same thing, we just do plug n equals back here. So this will become 4k plus 1 quantity square. And again, same justification for the numerator and then setting with these degrees. It's just the same as before. You just play with the different numbers. And so from here, that means that we can actually apply this substitutions. Let me actually first underline our left-hand side and then our right-hand side for these two terms. And so with that, we can actually plug in the substitutions back in for here. So meaning now we have a new rewritten S, capital S. So let's actually write this out and see that now so far we have that S is going to equal, so we plug in everything for odd. Well, okay, so this is going to be a little bit interesting, a little bit different since there's a k plus 1 for the ones that I just set the substitution for the n odds. What I'll do is that instead we have a k plus 1, I'll factor out a -1 outside, so that means that entire sum is going to be the same thing just like this, except that's a negative, but obviously that we have a 3 and then there's the 1 on the denominator over here, but that's the justification we're going to go with. So here, so we have, that means I'm going to put this term out first, and then we're going to subtract it with this term over here that's actually associated with the minus. So let's see, now we have, let's see, the infinite sum, k is equal 0 of -1 to the power k divided by 4k plus 1 square. Then now subtract with, so same terms, k is equal 0 of -1 to the power k and then divided by 4k, add this with 3 square. So now how do we actually proceed forward from here? So here's actually a little bit of, this is actually a little neat twist that involves, yet again, we actually have to do a little bit of rearranging of the indexes. So let's actually just do that. So I'm gonna first, we'll first do this one sum at a time from what we've written so far for S. So let's actually take a note that I'm gonna put an asterisk just for, to imply that a little note. So let's see, we have that, so I'll put k is equal 0. This is actually just, same thing as above. We're working with this term first before we move on to this. So we have -1 to the power k and then divided by 4k plus 1 square. You'll notice that we can separate this yet again from terms of even and odd terms. I know, again, right? But we notice that because with this alternating, so we have that the even terms are all positive. We just plug this back in, but then we also have, we plug odd terms, we get the negative. So we just add all the sum of the negatives that's supposed to be applied to the odd terms. So first we have that this is, k is even of the same, of our same series. And then of course, we're gonna subtract that with the, everything associated with the odd terms for k. So -1, k, and then divided by 4k plus 1 then square. And now similarly, the same thing can be said for this one over here. So we just separate this out by even and odd terms. So k is equal 0 of -1 to the power k divided by 4k plus 3, then quantity square. Separate this with the even and the odd terms. So now we have, this is going to be k is even of -1 to the power k divided by 4k plus 3, then square, and then subtract this with, everything for the odd terms, since everything from the numerators are all negative, so we can factor that out. So k odd, and then -1 to the power k divided by 4k plus 3 quantity square. Now here's, again, we're actually gonna have to do the same thing just like before from everything written in red. We're going to actually do a little bit of substitution in terms of the indices. So let's actually jump into that. Again, we'll do this one sum at a time just so we can see like what's happening over here. We're gonna let specifically, we'll start off with the 4k plus 1 denominator first. So if we look at k is equal to 2m plus 1, the k is odd. And then if I do the same thing, but except this is for even, so k is equal to 2m for k is even. And so here we're actually going to deal with a new sum. So over here, I'm just going to move this to this line over here. So now we're going to have this infinite sum, and just put back the -1 to the power k divided by 4k plus 1 square. So if I just put all this substitution for k equals 2m plus 1 for odds and then even, so now we would have this following sum. So we would have this infinite sum of, so now the new indices would be m is equal to 0 of 1 divided by 8m, add this with 1 square, then subtract with the infinite sum, and then put this back for the odd indices. So 1 divided by 8m, add this with 5, and then quantity square. And then the same thing can be applied for this same term over here for the 4k plus 3. So now we have our new sum, the infinite sum, k is equal 0, negative 1 to the power k divided by 4k, add this with 3, quantity square. Now we just actually just plug in that substitution back. M is equal 0, so now we have 1 divided by 8m, add this with 3, quantity square, and then subtract this with the infinite sum, m is equal 0 of, now there's going to be 1 divided by 8m, add this with 7, and then quantity square. Okay, so now with that, now let's actually, well, before we actually get to that substitution, there's actually, this is where now we're actually going to be using some special formulas to help apply evaluating these sums, specifically with these new substitutions. Before I do that, let me actually just underline what our new substitution is. So for these two sums over here. Okay, now with that, let's actually move on to that special formula. What we can do here is now by applying the polygamma function, the series representation of order s. So that formula says that for some psi, I'll put this order s of some complex value z, such that z can't be a negative integer, and then m, and then for situations m is or s is supposed to be greater than 0, that it's also an integer as well. If you think about this is like reading this as an order. So this is going to be equal to negative 1 to the power s plus 1 multiplied by s factorial, and then multiplied by this infinite sum with the m is equal 0 of 1 divided by m plus z, and then to the power s plus 1. And so from here, if we just let s equals 1, then now we have this, we actually give ourselves a little trigamma series. So z, and so that means we have this infinite sum of the following. M is equal 0, and that's just going to be square. So this will be 1 divided by m plus z, quantity square. Just like that. Now we can actually apply some formulas back into the substitution that we just did. We're going to start with this substitution over here. Now, if you notice that what I can do is if I expand this out and then you apply the FOIL method, you can actually factor out some, we can actually factor out a 64 on the bottom, because you look at it, it's like 8m, then multiply am plus 1 multiplied by 8m plus 1, so it's 64m. And then add this back with, 16m, and then divided by, plus 1. So in other words, well, actually, it's just, you can factor out the 64. It's just 8m plus am, factor out the 8s, and then just combine that back in. So same thing can be said for the rest of these, substitutions over here. So anyway, so what we have now, so we'll start off one sum at a time, is that the infinite sum of k is equal 0 of negative 1 to the power k divided by, or k plus 1 square, simply is just going to equal 1 over 64. Now factor out that 164, so now we have this infinite sum starting from m is equal 0 of 1 divided by m plus 1 over 8 square, then subtract with this infinite sum of, so same thing, and then divided by m plus, this will be 5 over 8 square. And now we can do the same thing for this one over here. So I'm going to utilize some roots. I'm going to put this over here. So infinity m is, or it's supposed to be k actually. K is equal 0 of negative 1 to the power k divided by 4k plus 3 square. Then that's going to equal, so apply the same thing. I'll factor out a 1 over 64. And so now this is the infinite sum of m is equal 0 of 1 divided by m plus 3 over 8 quantity square, then subtract with, so same sum, infinity, m is equal 0 of 1 divided by m plus, so this will be what, 7 over 8 square. And so from here, now we can actually apply this trigamma formula and do a little bit of substitution. So from here, now I'm gonna switch to a different marker and write the new, the new rewritten expression using the trigamma function. So now so far for this term over here, let me just take things one step. So this will be specifically 1 over 64 and then multiplied by the trigamma. So I'll write this as psi of 1 of our input's going to be 3 over 8 and then subtract with psi of 1 again, and then of 7 over 8. And over here, I'm just going to move to this line over here. So this is going to be written as 1 over 64. And now we have psi of order 1 of 1 over 8, then subtract with psi of order 1 of 5 over 8. And so from here, we can actually do these substitutions. And before we get to that, well, actually, no, let me actually write what we have so far. So that means S is equal to, so far it's the subtractions of these two, and then don't forget there's a 1 over 64. And I can actually distribute the negatives over here. So now, in other words, we'll have 1 over 64, then multiply by these psi, the sum and differences of psi. So order 1 of 1 over 8, or add this with psi of order 1 of 7 over 8, and then subtract 1 of, 3 over 8, then subtract psi of order 1 of 5 over 8. We can actually, now you might be thinking, how can we further evaluate this from here? Well, 2 more formulas we'll be using, well actually 1 formula, and then after using that 1 formula, we can actually do a little bit of differentiation. So right here, what we're gonna do is we'll be using the reflection formula for the digamma function that says that psi of 1 subtract z and then subtract psi of z is going to equal pi times cotangent of pi times z. And what I can do from here is, since we have these orders of 1, so we can treat it's more on the lines of differentiating. So if we were to differentiate both sides of this equation, so now we would have psi of order 1 of 1 subtract z, then add this with psi of 1 then times z. This is actually just going to equal to pi square. This is going to equal to pi square times cosecant square of pi times z. So that means we can actually do all this substitution. And so far now our S is going to equal this following. So we have S is, now after plugging in the right inputs, of course, so we're going to have pi square and divided by 64. Simply, I just factor out this because this is everything that's there. We're gonna have, this is cosecant square of pi over 8, and then next is subtract cosecant square of 3 pi over 8. And now from here, there's actually, the rest of this calculation relies a lot on some trigonometric identities. No worries, this is actually going to be not that difficult to see here. If we actually skip ahead, well, okay, so cosecant square of pi over 8 is the same thing as 1 divided by sine square of pi over 8. So I can apply that to the same thing for over here. So it's just 1 divided by sine square of this, and then minus 1 divided by sine square of this. But specifically, this can be rewritten using the symmetry identity for sine of pi over 2 minus theta is equal to cosine theta, and then you just square that. So now we have pi squared divided by 64, and then now we're gonna have this new identity. So this is 1 divided by sine square of pi over 8, and then subtract 1 divided by cosine square of pi divided by 8. So if we continue forward, then notice that let's actually apply the butterfly method. And so we have pi squared divided by 64. Then, so this would be cosine square of pi divided by 8. Subtract sine square of pi divided by 8. Then just combine these denominators together. So sine square pi over 8. Then multiply by cosine square pi over 8. Then if we actually just use a bunch of trig identities, specifically for one, that sine square of some input times cosine square of some input. Specifically, if we look at this as sine square of an input is 1 over 2 times 1 minus cosine of x, cosine of 2x, and then the other one's the same thing, but it's a plus cosine 2x, and you treat this as a like a difference of squares, but then the 1/2 multiplied together, so it'll be a 1/4. So after all that multiplication from this identity from the denominator, it's going to be 1/4 multiplied by 1 minus cosine square pi over 4. And if you want to rewrite this using the trig identity, so it's 1/4 times sine square pi over 4. And then for the numerator specifically, cosine square of some input minus sine square of some input is going to equal cosine of 2 times some input. So that's actually the trig identity we're going to go with over here. So now after all this, so we're going to have pi square divided by 64. Then we're going to have cosine of pi divided by 4, all this being divided by, well, this will be 1/4. That's fine. I'll write it like that's of sine of pi over 4. That's supposed to be a square over here, right? After all this, so we have a cosine and then a sine. So I can write 1/4 as 4 on the numerator. So, and factor out that 4 and that'll reduce to a 1/16. So in other words, pi squared divided by 16. And then on the bottom, we know that cosine of pi over 4 is just square root of 2 divided by 2. Same thing for pi, sine of pi over 4, that's the same thing, but squared that. So in other words, you're gonna get a, it's going to be a 1/2 on the bottom. And so if you just flip that reciprocal, then we have the 2's will cancel. And so we're left with a square root of 2 on the numerator. So that means I have times the square root of 2, or how about right? Well, let me first put it this way. I'll write this as the square root of 2 divided by 2, and then on the bottom is going to be 1/2. And so therefore, the 2's will cancel, and so therefore we're left with our final answer of pi squared times the square root of 2 divided by 16. And just like that, that is actually our final answer for this special alternating sum. So if I went a little too fast, I apologize for that, but I'm sure that these substitutions that I made, that I skipped a couple steps, I'm pretty sure they're straightforward because obviously these are just simple trig identities that anybody, I know that you guys know it too, especially. But the other functions I use, like digamma, trigamma, the polygamma functions, is a little bit different, especially for any of the new viewers who are not, well versed in this kind of function. So it's best to, explain it a little further. Now with that, we have all these substitutions that we make, a lot of rearrangements with the re-indexing. So that's, yeah, you can see why my board is very much filled up. So yeah, that's pretty cool if you ask me.